energy balance. So the key ideas of boundary theory, as I have we considered the example of flow past a flat plate. So the key idea is the separation of scales, distance and time scales. So we said that the boundary thickness, which is the characteristic dimension in the y direction, so the plane is like this, and the fluid is predominantly flowing in the x direction. So this is the x direction, y direction. This would be the length of the plane. The length is the scale in the x direction. The characteristic scale in the y direction is the boundary thickness. And the boundary thickness is generally regarded as being much smaller than that of the length of the plane. This then we saw actually doing a sort of an approximate order of magnitude analysis leads to the using the continuity equation. This would mean that Ey, that is the velocity in the characteristic velocities in the y direction, are of the order of dx given multiplied by delta by L, which means that the ratio dy to dx will be of the same order as delta by L, which means that the velocity components in the y direction induced by the flow past the plane would be much smaller than the velocity in the x direction. Then using similar kind of analysis, the non-dimensionalizing and then looking at the order of the terms, we also found that importantly, this is an important relation, that the boundary thickness at a length L would be of the order of the Reynolds number raised to the power minus half. The Reynolds number itself is defined so that it depends on the distance x. We need to be careful that REL is given by L. We can take this as the characteristic velocity itself, and by the kinematic viscosity. So from this I can conclude that the boundary thickness at any distance x divided by x would be of the order of the Reynolds number raised to the power minus half. We put all these approximate analysis into the momentum equations, especially the x direction momentum equation in the non-dimensional variables would look like this. Doesn't have any of the parameters because of the use of all these relations. And finally, when I convert it to the actual variables, all you will get is the kinematic viscosity into the equation. So this is often referred to as the boundary layer equation. This I didn't prove this final step, but you can easily verify. You have to also use these expressions while doing that, then you will get the answer. But anyway, more than the proof, the final equation is very important. It has both dx and dy appearing. We need to strictly consider what happens in the y direction, the momentum magnitude in the y direction. I'm not going to get into that. So by using the stream function, we can get both dx and dy. And so the stream function, as we do for this case, the planar flow is defined in such a way that d psi by dx is d1 and d psi by d1 is minus dx. So if you put that into this equation, then you get the following third order partial differential equation in psi, and that will look like this. We have looked at this also in the previous class. So the question is now how do we solve this? So this belongs to some class of PDEs which can be solved by the similarity transformation. And general approach is to propose that psi would be of the following form. And then the E itself is proportional to y times x power minus q. And then you find exponents p and q so that this partial differential equation of psi in x and y reduces to an ordinary differential equation of f in terms of eta. So I'm not going to explain all the steps how to find a p and q in a general case, but in this case it can be shown the following forms. Constants also have to come in. These are the forms. So this form, this is very standard available in all the textbooks, right? So x power half, so here p is equal to half, and then the eta itself can be shown to have the form q itself also is equal to half, because I put minus 2 there. So now the question is how do we convert this? I'm not going to go through all these steps, but clearly what I guess, are there any questions? I heard some rumblings anyway. So this is just, you have to take it as given. You have to take it as given. But given this, you should be able to derive the ordinary differential equation for f. Okay? So I just outlined the first one or two steps, and then it's just a question of repeated differentiation, right? So what we need clearly is first d psi by dx. I just calculate d psi by dx and d psi by dy. Those are very important also for the fact that they directly give the velocities in the two directions, right? So d psi by dx is square root of, this is a constant, right? And so this will have two terms because eta is also a function of x. So that's where the catch is. So you have to be very careful about that. This can be written as x power half times f prime of eta. So I'm doing the product rule. X power half. So I'm not differentiating this. This first differentiated with respect to eta, and clearly then I have to put the eta by dx, right? Plus then f of eta times x power half, that would be 1 over 2x. This is what I am getting. Then d psi by dy is somewhat easier to differentiate because the x here doesn't have to be differentiated. So the idea here is that the dependence of x is here, and there is both the dependence of x as well as y here. That is why it's important to where the chain rule would come in, right? So now, with respect to y, I don't have to differentiate the x because this is keeping x fixed, and then I would have x prime of eta again times d eta by dy. All the derivatives with respect to y are going to be easier to evaluate, right? Anything with respect to x would involve slightly more complicated, and d eta by dx and d eta by dy can be easily derived. By dx is going to be square root of g naught by y, right? Minus half x power minus 3 by 2 d eta by dy would be square root of, taking what we called earlier as a characteristic velocity, the x direction, that is dx. That is what I am now taking it as this so-called free stream velocity once and for all, because we need to get into the actual problem, right? So I have chosen that, right? So that's also the notation is also easier to see that that's a constant fixed quantity, and then I have x power minus half. If I put both of these into this, I just write the final expression. What we get is d psi by dx, which is equal to actually dy, is given by minus half square root. Just simplify all of this, then you will get we easily prove this, and then d psi by dy is equal to actually minus dx, and f prime of eta. So we are not going to be too concerned about dy here for now. So this is obviously going to be a very important relation which says that dx by d naught is equal to f prime of eta. That is the scale, the derivative of f with respect to eta is nothing but the scale velocity in the x direction scaled by the characteristic velocity. Right? That's easy. You should be able to very easily prove it. But the rest of the completion of the problem depends on now calculating d squared psi by dy squared, d squared psi by dx dy. Those are going to be slightly more complicated. You have to do it very carefully with the appearance of these coefficients, and then all of this will make it a bit more complicated. But I want you to do that as an exercise. The final equation is strikingly simple, and that is given by the following equation. Has to be here. 2 times d2 f by d eta 2 plus f d squared f by d eta squared equal to 0. This is what I am getting. A lot of the terms would just cancel out. This is the final equation of f. Again, it's not easily solvable analytically. All we have done is converted a partial differential equation to an ordinary differential equation. Still, this is going to be easier to solve even numerically, which is what we have to do. Compared to that, right? There is a simplification. This is still a nonlinear equation, and we have to solve this. Now, what are the boundary conditions in this case? Right? First, the boundary conditions that we express in terms of v's, the velocity components, right? And then in terms of f. So let's look at the boundary condition. I'm going to erase this. Let's say at this point at x equal to 0, right? Dx doesn't mean dv by dx, it's the x component of the velocity. X equal to 0, y is equal to v naught. So here you could see, if we are going to convert it to an expression in terms of eta, f of eta, we would have to consider, we cannot consider y equal to 0 because eta, not against everything. Eta is actually given by square root of so anyway, we first write it down. Then comes the no slip condition. The no slip conditions for Vx would be at y equal to 0. Why? Because incomplete linear we discussed fluid, completely bending the surface, so most of the conditions are met. There's no question of not applying. So also equal to 0. And we need the one more condition that is often written. For instance, if I have a profile like this, and then I say that at any point, right, x within the velocity profile will look like this, and it will tend towards v naught as y goes to infinity. So I can write Vx at any x y goes to infinity is also equal to v naught. Right? So these are the boundary conditions. So let's see how this will translate. So I have to be a bit when I put x equal to 0. I actually have to consider y not equal to 0, right? So y is finite quantity, I will assume. When x equal to 0, clearly eta becomes infinity, right? So this would be the geometry, eta going to be infinity, right? And dx is nothing but v naught times f prime of eta, right? So dx by v naught goes to 1. So I have f prime of eta goes to the limit is equal to 1. Eta goes to infinity. That's what I have. Now let's look at this. So again, when I come to y equal to 0, I will simply have to take eta equal to 0. I'm not going to consider the case what happens when x is equal to 0. So we are obviously considering all x greater than 0, applying that condition. Right? So because I don't want to get into a problem with 0 by 0, 0 by infinity and so on. Right? So y equal to 0 clearly corresponds to eta equal to 0 but all positive x. That's clear, right? So both of these would have eta going to 0. So what can you say about Bx? So clearly f prime of 0 is equal to 0. What can you say about By? Right? So By is given by this. Right? So if this is, again as I said, x is non-zero. So this is remaining as it is, some value of x at any value of x. Now f prime of eta, so I'm looking at this By, what happens when y equal to 0, which means eta equal to 0. So I have to look at this formula. Right? So as eta goes to 0, this is 0. F prime of eta is finite because I have just shown that f prime of 0 is equal to 0 from the Moseley condition applying to Bx. So this is finite. So 0 times 0, so that's 0. So if By is 0 and eta equal to 0, I get that f of 0 is also equal to 0. Y equal to 0 corresponds to eta equal to 0 because eta is simply proportional to y. Right? And so what this means, so this is the effect of the no-slip condition. The no-slip condition on the velocity implies that both f as well as its first derivative with respect to eta vanish when eta equal to 0. And then you can easily prove that this y going to infinity will effectively give the same condition. So I don't have to, I don't get anything different from this. And so this is a third order differential equation. So I have three conditions. So this is like an initial boundary value, probably you can say, but the boundary is actually eta going to be infinite. Right? The solution is numerical, and there are many books give numerical values of the function. So I looked at, for instance, a book by Cox and McDonald as a table of f. What they have, I just write down. At eta equal to 0, we know that f prime on 0. That would be the conditions used to solve the equation. That is there. And then they give that f double prime of 0 is actually 0.332. Numerically, if you solve, so you have to first solve for f, and then you can find f prime and f double prime, which is probably also needed. Right? And then at eta equal to 5, if you see, you have f is equal to 3.833, whatever that means. F prime is equal to 0.9915 and f double prime 0.0159. And eta equal to 5, and actually this alone will be important. You see, because commonly, even though we have here that as y goes to infinity, dx goes to b naught, right? The boundary layer could be as an approximation. We say that what is delta? Right? What is delta? Delta we haven't yet defined actually clearly. Right? The delta is sometimes it is taken when y equal to delta at any x. Y at y equal to delta, dx is actually equal to 0.99. It's a common definition used that when we get 99% of the free stream velocity, we take that as defining the boundary layer thickness. So delta obviously also depends on x. Y equal to delta. At that particular location, we take when the velocity reaches the 99% of the free space velocity, that we take as delta. So how do I apply that here? Because I know that f prime is nothing but dx by d naught. So what I am getting here is that at eta equal to 5, dx by d naught is approximately, it's not exactly 0.98, it's 0.9915. This can be a rough, I didn't find anything corresponding exactly 0.99. Right? So this is an approximate. And so what is eta? Right? So eta is square root of, so I can say square root of V naught by the kinematic viscosity times x power minus half, right? That is eta equal to 5, right? And what would you substitute for y? Because dx is 99% approximately, I can approximately make y to be simply delta. That's by definition. Right? So this is what I am getting. This is equal to 5. Now from this, we get that delta is actually equal to delta of x, that is delta evaluated at corresponding to the distance x from the leading edge is actually given by 5 times square root of divided, so that would be x power half. It's increasing as you expect in the way of a square root, but delta by x you can see is given by 5 times square root of, I have to divide by x, so this will become x power minus half, and so the x can be brought into the square root in the denominator, and this is nothing but, so we sort of recover what we inferred from purely a dimensional type of analysis, an order of magnitude estimate. Recovered and got that as the defining equation, but this is an approximate, and what Lightfoot and all the other books give is that the actual one, if you just adjust the fact that we have actually used 0.9915 to adjust the eta and look for the one that would give f prime of eta to be exactly 1, as close to 1 as possible, then it is given by 4.64 Rex per minus r rather than 5. So that sort of completes the finding of delta, right? So now this is you can clearly verify this with Birch to Lightfoot. But Birch to Lightfoot interestingly also given expression for Ex. They say that Ex by V naught. So again the standard expression might differ slightly in other books. This is how he gives the. So you have to understand that Ex is a function of both x and y. Right? So this is again can be considered because only y appears explicitly, but delta is a function of x. So strictly to avoid confusion, I have to write it like this. The x dependence sort of concealed. Delta is just a convenient way of writing it. Now if you substitute this value of delta here, you will actually find that y by delta is actually eta by 4.64. The 4.64 that comes there will appear down here. So all effectively what you Lightfoot are saying is that Ex by V naught is 3 by 2 eta by 4.64 minus half eta by 4.64 the whole cube. So what one could say there is nothing particularly striking. This is just a polynomial representation of f prime of eta, an approximate based on the numerical simulation. That is what I can say. There's nothing particularly fundamental about this kind of y over delta minus y over delta cube. It's just an approximate way of representing f prime of eta, because if you see that y over delta is actually coming out to be eta by 4.64, this is entirely a function of eta. That's exactly what the f prime of eta is. So this is nothing more than a polynomial numerical representation of f prime of eta. It's approximate and nothing particularly fundamental about the coefficients 3 by 2 and half, or even about this kind of a dependence. that's what I would think. And in fact, you can very clearly see that no longer this condition will apply. Eta going to infinity has no meaning here. The eta cannot go arbitrarily to infinity in this form. This is approximate, right? So if you look at this, another bracket here. Too many brackets, so I think now it is fine, right? You can see here, when would Vx become equal to V naught? When y becomes equal to delta, so that is taken care of here, right? So Vx equal to V naught. So this is again the point of, I'm sorry, this 3 by 2 should come here. No need for an overall bracket. Right? So 3 by 2 multiplies the first term, and then I have minus half. So there's some, of course, it's not really, because we said first of all that Vx by delta is different when Vx is 0.99. But finally, when the approximate expression that virtually I should give, it actually becomes exactly equal to V naught, right? That's again a further approximation, right? So 0.99 here. So this sort of, so we are simply approximating the eta going to infinity limit, or rather the y going to infinity is approximated as simply y equal to delta. But numerically I have to stop somewhere. Right? So for that I use the 0.99%. So there's a lot of approximation involved. So this is convenient finally to use. Right? So we proceed with this for the rest of the calculus. Are there any questions? This can be a bit confusing. We have to see how the delta was first obtained by using this 99%. But finally you see that this approximate, so clearly this is an approximate, can be very clearly seen. In this approximate expression actually Vx becomes exactly equal to V naught, not 0.99 and y equal to delta. So there is some contradiction with this. Right? So this is part of the approximate analysis. This is merely a representation for Vx that's useful for practical calculation. That's all. So with that, we have this, then Vy we are not going to get into it. Maybe I'll put that all in the assignment and let you work out what Vy would look like. Now, another important point is the range over which, because we made this approximation that delta by L is less than or equal to 1. Right? So there are some different values you get on what range of Reynolds numbers would this really be applicable, these equations. We haven't really said, we said that starting, we neglected the inertial terms. Creeping flow corresponds to very low Reynolds numbers, but with very high Reynolds numbers we approximated using the boundary layer equation. But how high can it be? Can it be by any arbitrarily high Reynolds number? That's not what it is. The flow through a wave, in fact, Lightfoot would say that Reynolds number has to be greater than, these are approximately valid for Reynolds number greater than 10 power 4. Probably correspond to REL, or maybe the range of Reynolds numbers has to be in this range, 10 power 4. And then he says that get the exact number that he has. And he further says that somewhere greater than Reynolds number equal to 10 power 6. So these equations can be valid, but then what is the higher limit? So he says that for Reynolds number greater than around 10 power 6, the flow is becomes turbulent, and you have to take into account the effects of turbulence. So this can be roughly in the range of 10 power 4 to 10 power 6. It's meant to be formulated, which is generally expected to be valid. Again, a rough, because it's not a simple Reynolds number, it's actually depending on L. So we can take that to the REL if you wish. Roughly, we have to check REX to REL, how much it actually, the Reynolds number obviously will be very low here. Because X is here, A is defined, but once you given at some point close to the edge, it has to have a certain number close to 10 power 4. Otherwise, we cannot use these equations. Right? That is roughly the idea behind the boundary layer. Now we can end this by also calculating this another important calculation, and that is the force, the contact force due to the boundary layer flow. Contact force, as we have seen, you fall back on the familiar expression, the final expression is given in Lightfoot. So here n is clearly equal to Ey. If you look at it as the force exerted by the fluid on the plate, the output normally would be in the positive y direction. And clearly then n dot t, and obviously this whole thing has to be at y equal to 0, because that is the force exerted on the plate, the fluid layer immediately adjacent to the plate, right? And dA then clearly would be dx dz, and I can put the limits for dx, x would be from 0 to the length of the plate. If I assume that the width of the plate, that would be the z direction, this w, those would be the limits, and clearly then n dot t will get only the second row of this stress tensor. So it will be Eyx Ex plus Eyy Ey plus Eyz Ez. Eyz can be very easy, it's going to be 0. There is no effect of any variation. Either Ez is 0, there is no variation with respect to z of either of the two velocity profiles. So you can easily verify Eyz would be 0. There will be no component in the force in the z direction. Eyx would turn out to be, for the linear with the Stewart, and Eyy would be minus t plus. And however, if you, what we want on the expression that y equal to 0, at y equal to 0, it can be easily shown that both the derivatives of Ey as well as Ex with respect to y would vanish. Have to prove that, right? So I would not look at that now, but then you have the x direction. You have the quantity coming from dx by dy, and the y direction will have the normal force coming from the pressure. And normally, what the expression is given in verse corresponds only to the so-called tangential or maybe shear force, and not the normal force. So I can like the x component alone is what is the expression that is commonly found in the books, and 0 to w, the integral over z will simply give me w, and then I get 0 to L viscosity can also be dx by dy at y equal to 0 times dx. This is going to be purely an integral over x alone. Now there are two ways of doing it. So I can directly differentiate here, right? Dx by d naught is equal to 3 by 2. Since it's derivative only with respect to y, it is quite easy to do it. So this will be 3 by 2 times 1 over delta. Derivative with respect to y, right? So I have to very carefully. Dx by dy is d naught times 3 by 2 times 1 over delta minus half 3y squared by delta cube. But if I want to evaluate it y equal to 0, this term vanishes and I simply get 3 d naught by 2 delta. Of course, delta, for that I can 3 by 2 d naught, and 1 over delta is simply, so you have to be a bit careful, right? So delta is here 4.64 x times Ravi x power. I can actually directly use this instead of 4.64 here. I can use this. So delta would be 4.64 times square root times I will get x power half. So what I need is 1 over delta, so I need to substitute that here. Okay. So if you put that and differentiate, all I have to do is integrate x power half. That's very easy to do, right? But x power minus half, because I have 1 over delta, right? It will be x power minus half. Okay, so I have to integrate that. The final answer turns out to be 0.647. Expression in Wordsworth Lightfoot is 0.664 times, rather I would like to put 1.38 times square root of rho L V naught Q is what he has. So now this is fine. Rho is within the square root. L is also within the square root. The dynamic stuff is also within the square root. W is here as it is, so when it goes into the square root, it becomes W square. V naught is actually 3 power 2. So when it goes within the square root, it becomes V naught 2. So this is fine as far as the dependence on the input. What about 1.38? Now this actually corresponds to it on both sides of the way. That's what he has the expression for. So the calculation, what we have done so far, 0.647 is for the force exerted by the fluid on one side of the plane, but the plane is actually immersed in the fluid and we have fluid flowing all over the plane. So the same analysis would apply for the boundary layer on the other side of the plane, and so you would get 2 times this. That's what this is, but this is 0.647. 2 times that is not exactly 1.328. That difference comes because I think what he has done is used the other expression here. What he has used is actually, if you differentiate this with respect to y, right, this will be V naught, right, f double prime of eta, then d eta by d1. So d eta by d1 is square root of V naught by the Gell-Mann viscosity, right, times x power minus half. Now at y equal to 0, this would be simply eta equal to 0. Now if you look at again any of the tables, for the Fox and McDonald, give f double prime of 0 as 0.332. So if you use that, twice the 2 will come from the integration x power minus half to be x power half divided by half. There will be a factor of 2 coming from that. So this would become 0.664 if I use that. There's some slight discrepancy in these values, right? And you will finally get 1.328. So that comes because there are some approximations involved. It's not exactly consistent. So that's a very minor difference. What is important is not the coefficient, but the somewhat complicated dependence of the force on all these variables: density, the dynamic viscosity, the width, and the velocity. I cannot give any physical explanation for all these dependencies, but we'll just leave it at that. Width is probably easy to get, but even length is like a square root of L, because things are varying along the L, the x direction. So you have to get the integrated value. It gives rise to a square root of L dependent. Width is simply going to be proportional to the width, whatever the width is, because that doesn't play any role in the, there are no variations in that, in this integration. In calculation of the force, because it is evaluated at y equals z over the z. There is no dependence on the z of any of the quantities, so that just gets factored out of the integral. Are there any questions? So with this we wind up the boundary layer theory, because it must be fairly well known to most of you from your earlier courses on fluid mechanics, and I just wanted to highlight certain important aspects of it. It is somewhat in line with the point that we made about irrotational flow and how the solid surface for a linearly displaced fluid cannot have irrotational flow throughout. So this sort of fits into that line of thought, right? It's an approximate analysis, so we have to keep in mind all the approximations and finally how we have resolved it and got something concrete to work with. Okay. So there are no questions. Then we move on to the next topic. We still have about 5 minutes. I don't want to waste that time. Move on to energy balance. So we've looked at the balance of mass, balance of momentum. So far we have not looked at the energy balance. Effectively we have assumed all the fluid flows to be at a fixed temperature, so that we do not have to bring in the temperature as a variable. Right? So everything is sort of suppressed, and so when that cannot be assumed, right, then we would have to bring in the energy balance, the scalar balance. So if you have one equation, contrast the momentum balance, this is somewhat like the mass balance. So the energy balance, if you recall the first law of thermodynamics as it arose, most of you who have taken the thermodynamics course would know that the first law of thermodynamics can be written as the time derivative of the internal energy is given. This is the first form in which the first law of thermodynamics came. Now, what is has many restrictions. One is the body is homogeneous with respect to temperature and density. So fixed temperature and density, and also it's a closed system. It's a fixed mass, right? So there are no temperature gradients, there are no density gradients, which we know cannot be true in general. Because when you heat a body, it's going to expand. It doesn't mean that it won't induce any density gradients, nor would the heating be such as to maintain the temperature to be uniform throughout the fluid. Both are approximations. And so only the special class of fluids, the homogeneous throughout, whatever may be the action that you do, whether you do work or you provide heat or you apply work on the body. And further, the first of thermodynamics means fixed mass, closed system, and also it was allowed only for reversible processes, which means effectively WR was taken to be E times dE by dt. The QR had a similar was used in the obtaining the first law of thermodynamics based on the axioms of Cont'd and Clausius, and to some extent Joule and May. Right? So now this we have to generalize this, because we are not considering closed systems. We are having fluid flowing through, right? And we also have to take into account the effect of the fluid motion, right? And plus, we also cannot be constrained to reversible work and heat addition. So it has to be somewhat more general than this. But this is the starting point. So whenever I generalize some expression coming out of a closed system analysis, here we replace it by what is happening to the body as a whole, which we can isolate within the fluid. So the first generalization will come in that the derivative here would be the substantial derivative. So now as always, as we saw the first application of the proposal of the conservation of mass was in this form, right? Application of the momentum balance was in this form, is equal to dA plus rho p dV. That is the rate of change of momentum of the body is equal to the net forces acting on the body. We consider two kinds of forces. Now when we come to the energy balance, again we propose something to the body as a whole, from which we will derive the local energy balance, and from which we can extend it to obtain the energy balance for any controlled volume, right? So here would be the internal energy, would figure in origins from the first law of thermodynamics of a very special class of systems, but I also have to now include the kinetic energy of the body, which is neglected in classical thermodynamics. In classical thermodynamics, we say that the fluid is expanding so slowly, that is the meaning given to the reversible process. Strictly, actually, nothing should happen, right? These equations are somewhat misleading and gives the impression that something is happening in time, which it is, but strictly we end up calculating only changes, and the time sort of drops out of the whole analysis. That cannot be the case in general. The kinetic energy would have to come into the picture. That is neglected there, right? When we consider some fluid expanding against the piston, the typical situation considered in classical thermodynamics, we don't associate any energy of motion of the system as a whole, right? So that now will simply be put it as QR minus WR. It's a very general expression. It doesn't give much more information on how now we are going to express WR, since we don't want to be constrained to the reversible process. What are we going to do about QR? Because now this in any case will not apply, because this assumes that it applies the volume of the body as a whole, which means that there are no density gradients. Only the volume is changing, right? So I can replace, because it's a fixed mass, there are no density gradients. I have to consider only the volume of the body as a whole, not what is happening within the system. In the same way, this corresponds to the temperature of the body as a whole. Now we cannot be restrained by such a situation, because we want to consider conduction and so on. We have to consider temperature variations, right? So how are we going to account for that? We start in tomorrow's class.